In this next chapter, we're talking about Maxwell's equations and electromagnetic waves. These equations we are, for the most part, familiar with already. The first one, we talked about Gauss's law for electric flux. So we said the electric flux through a closed surface, that's the circle on the integral. The electric flux through a closed surface depended upon the net charge located inside the surface. So we could write this flux as the integral of E dot dA over a closed surface, or we could write it as the charge inside that surface divided by epsilon naught. Second equation is Gauss's law for magnetism. The flux through a closed surface, so looking at the flow of magnetic field lines through the surface, equals zero. Equals zero because we cannot isolate a magnetic north pole from its south pole. Magnetic field lines are continuous. If they come out on one portion of the closed surface, they enter in at another portion. Faraday's law is what we've just been looking at. Faraday's law is induced voltage, or EMF. So the induced voltage, well, I should put it over on this side. Induced voltage we've been talking about as the change in flux with respect to time. That negative sign is that the induced voltage opposed the change in flux. Now that was specific for one loop at a time. We did include an N to account for how many times a wire or a coil looped around. But fundamentally, the changing magnetic flux created an electric field. Now the last equation is the one that's a little bit different. We saw Ampere's law as the line integral of the magnetic field along a path was equal to mu naught times the current flowing through that path. Turns out that's not complete. Maxwell determined that not only does a current create a magnetic field, but so does a changing electric flux. So what we see is that a changing magnetic flux created an electric field, but it turns out a changing electric flux creates a magnetic field. Some place that we would see this is between the plates of a capacitor. So if we have a circuit and we have a capacitor in the circuit and a resistor or something like an RC circuit, during the time that the capacitor is charging, while the charge is changing on the plates. So we know the charge on the plates of a capacitor is equal to C times the potential difference across the plates of the capacitor. The rate at which that charge is changing, so how fast the capacitor is charging or discharging, also creates a magnetic field. So if you recall, if there's charge on the plates of the capacitor, there's an electric field in here. If that electric field is changing, there will be a magnetic field circling that changing electric field. So changing electric flux will cause a changing magnetic field. We can write this is the rate of charging or discharging. We know if we take the capacitor and disconnect it from the battery, the charge will leave the capacitor. It will discharge until it reaches an equilibrium. So dq dt, this charge needs to be changing because that's why the electric field would be changing. If you recall, the electric field between the plates of a capacitor was equal to the surface charge density divided by epsilon naught. But surface charge density was charge per area. Oops, sorry. If we solve for Q here, E times A is the flux, the electric flux. So we can write also dq dt, which means the same thing as the change in electric flux with respect to time. This rate at which the flux is changing, the charge is changing, is called a displacement current. That terminology is a little misleading in that there's no actual charge traveling from one plate to the other. This displacement current represents how fast the charge on the plates of the capacitor are either increasing or decreasing. And so it's this term that needed to be added to Ampere's law up here. It's now called the Ampere-Maxwell law because Maxwell was the one that recognized it was not complete to begin with. So if you notice, this term has a mu naught times epsilon naught times d phi dt, where this is specifically electric flux. That's what we just saw down here, is that the rate at which the charge changes is our constant epsilon naught times d phi dt. So ultimately what we see is that electric fields and magnetic fields go hand in hand. If we have a changing magnetic field, then we create an electric field. If we have a changing electric field, we create a magnetic field. These equations are called Maxwell's equations because he learned and noticed that if these equations were written in differential form, in terms of derivatives, so these deltas in here represent partial derivatives. We talked briefly about those when we talked about finding the electric field from an electric potential. Taking those four equations and writing them in terms of these partial derivatives, the form of these equations matches the form of the differential equations that represent traveling waves. In these traveling waves, they're very similar. The traveling waves, though, if you recall, we talked about waves early in the semester. A wave had some sort of displacement, and that function that described the displacement had to depend both on position and time. So traveling wave, the way that I've written this equation implies the waves traveling along the x-axis. If you recall, k was a wave number, which was 2 pi over wavelength. Omega is angular frequency, 2 pi times frequency. Phi naught is a phase shift, just to satisfy the initial conditions. A is the amplitude, which meant the maximum displacement, because this function was describing the displacement of the medium. Well, with this having the same form, Maxwell discovered that an oscillating charge, so an oscillating charge, source of charge, create electromagnetic waves. Now, I don't in any way expect you to know the solution to these differential equations, but these functions look just like the traveling wave functions. That means an electromagnetic wave will have a portion that is an electric field and a portion that is a magnetic field. At the moment, I'm just writing it as a function of x and t, similar to as I did with the traveling wave. This would imply the waves are traveling, or the wave is traveling in just the x direction. E naught is the maximum value of the electric field. I'll write that out. That's the amplitude, meaning the maximum value. So in a given electromagnetic wave, there will be a max or peak value, the biggest value that the electric field will have. Similarly, B naught represents the maximum value of the magnetic field. K is still what we call a wave number. It is related inversely to the wavelength of the wave. Omega is still angular frequency, related to regular frequency in hertz. Phi naught is still a phase shift, representing a specific initial condition. Sorry, I don't know why that wasn't coming to me. Now, another interesting thing, when we compare this back to the equations describing traveling waves, it turns out that this portion represents a 1 over c squared. Meaning 1 over c squared is equal to 1 over that constant epsilon naught we see a lot in electricity, and then mu naught, the permeability of free space, where we saw with magnetism a lot. So, oh, actually, this is backwards. Sorry. I'm thinking about this original equation. Right here, 1 over c squared would equal, okay, this is where I got confused. I wasn't paying attention to the denominators in here. We have the 1 over c squared equal to, or next to the second derivative of the electric field with respect to time. But over here, in this other equation, they have swapped which side with respect to time versus with respect to x is. So I actually have to bring this to the other side to compare it to here in my first equation. So I actually find that 1 over c squared is equal to epsilon naught mu naught. So I apologize, I didn't look at my variables very closely. What this tells me, though, is c, the speed of our wave, which is the speed of an electromagnetic wave. If you happen to recall, we briefly introduced electromagnetic waves earlier on in the semester, And we said that they all travel at the speed of light in a vacuum, and we use c to represent that. So just to show this, epsilon naught, 8.85 times 10 to the negative 12, times mu naught, when I plug this in, I get lots of numbers. 299863381, which of course is not what we're going to use all the time. This is essentially 3 times 10 to the 8th. Now it should have units of meters per second, because this is a speed, and this is the speed of light. Experimentally, the speed of light had been determined before Maxwell's equations, but getting these equations and recognizing that the speed of light was dependent on these constants, or determined by these constants, was a big deal. So we have electromagnetic waves. Electromagnetic waves are created by oscillating charges. One other thing to look at is how the electric field and magnetic field are related to each other in this wave. So I'm going to grab a picture to show you. So I pulled this figure from our textbook. They're showing us what this sinusoidal electromagnetic wave would look like. And this is based off of a wave traveling in the x direction. That's what this V sub EM means. So this particular wave would be traveling in the x direction, but the electric field portion and magnetic field portion at any one location are perpendicular to each other. That is something that is always true for any given electromagnetic wave. So the direction of the electric field and the direction of the magnetic field are perpendicular. They're 90 degrees apart. In fact, the direction of travel, so the direction of travel, the velocity, is determined by the direction of the electric field crossed with the magnetic field. So right-hand rule, same one we were using in previous chapters in terms of cross products. If we put our thumb of our right hand in the direction of E and our pointer finger or index finger in the direction of B, our middle finger, if we're holding it perpendicular to our thumb and pointer finger, will give us the direction of V. Okay, so E and B are perpendicular to each other. Now the fields themselves are not displacing some sort of medium. When we look back at the graph and we look up, say up here, this represents the maximum value of the electric field, but there's nothing that's actually oscillating upwards in that direction. What that is telling me is at the location on the axis directly below E, so right there at this point on the axis, that vector represents the strength of the electric field and the direction the electric field is pointing in. Similarly, at this location on the axis, the magnetic field vector coming out to here, that represents the strength of the field and the direction that the magnetic field is pointing in at this point on the axis itself. So there's no actual physical medium oscillating up and down. These arrows represent the strength of the fields, the electric or magnetic fields, and the directions they point in at those specific points. Now, wavelength, if you recall from earlier in this semester, wavelength is measured peak to peak or trough to trough, any one point in the wave to that identical point the next time we reach that next point in the peak or the wave. Another thing to notice is that the electric field and magnetic field are in phase with each other. So E and B are in phase, meaning there's zero at the same time, their maximum values at the same time. They don't have the same maximum value, but if the electric field is maximum, then so is the magnetic field. So both E and B are maximum at the same time, they're zero at the same time. One other thing is that the ratio of the maximum electric field over the maximum magnetic field is equal to the speed of light, c. So that means the electric field is always 3 times 10 to the 8th bigger than the magnetic field. Okay, we'll talk about some other characteristics of our waves in the next video, and we'll do some examples with solving problems, that sort of thing.